this ordinary differential equation. So second derivative of bending moment is equal to 6x squared minus 36x, and the initial values of the bending moment and its derivative are also given. The first question is to solve this using the Laplace transform. So I would say that the two difficulties here are, first of all, that there's going to be three difficulties. The first one is that it's x instead of t. The second is that when you're looking for the formula to send x squared, you have to use the t to the n, because you have to understand that the role of t is being played by x. Laplace transform is 1 over s to the power of n plus 1. I'm surely that's not right. N factorial over s to the power of n plus 1. Right. So we'll take the Laplace transform on both sides now. Our little f here is m. So if you look in your tables on page 230, this is s squared times big M of s minus s times little m of 0 minus m dashed of 0 equal to, fix the 6, x squared is like a t squared, so it's going to go to x to the 2 factorial, over s to the power of 2 plus 1, which is 3. And then you also have minus 36. Now what about that x? Now x, if you're to put it in this framework, is just like an x to the 1, so it's like a t to the 1. So it'll be 1 factorial over s to the power of 2. Okay, so that's step 1, that's good. This is 6 multiplied by this. So now we're going to apply our initial conditions. That says m of 0 is 0. So this is s by 0, that's gone. M dashed of 0 is 108. So we have s squared times big M of s minus 108. 2 factorial is 2 by 1 is 2. 6 by 2 is 12. 12 divided by s cubed. 36 by 1 factorial is just 36 divided by s squared. We're trying to solve for big M of s, so add 108 to both sides. So you get s squared times big M of s equal to 12 divided by s cubed minus 36 divided by s squared plus 108. And now the other thing we're trying to solve for big M of s, we need to get rid of that multiplied by s squared. We must divide both sides by s squared, and this is probably the third place where this is a little bit tricky to kind of make up for the parts A and B, which are a bit easy. So you've got dividing both sides by s squared. You have big M of s here. So 12 divided by s cubed and divided by s 2 more times, it's divided by s 5 times. Okay, minus 36 divided by s squared twice, and now divided by s squared twice more, it'll be divided by s 4 times. And finally the easy one, 108 over s squared. Now we need to send these back. They're all easy to send back. There's no partial fractions here, and we just have that 1 over s to the n gets sent back to by the inverse Laplace transform. This is in the tables. T to the power of n minus 1 reduced to the power by 1 divides by n minus 1 factorial. Okay, now the other thing is I've got t's here, but of course we're going back to x. So we're going to go back from big M of s to little m of x, using the inverse Laplace transform. So I'm just going to write that there for myself. I like to do that. Okay, equals, fix the 12. 1 over s to the 5 goes to not t, but x to the 4 over 4 factorial. Fix the minus 36. 1 over s to the 4 goes to t to the 3, well, x to the 3 over 3 factorial, and finally plus 108, fix the 108, 1 over s squared goes back to t to the 1, x to the 1 over 1 factorial. And then we tidy this up 4 factorial is 4, you can get it on the calculator, but it's 4 by 3 by 2 by 1 is 24. 12 over 24 is a half. 3 factorial is 3 by 2 by 1 is 6. 36 divided by 6 is 6. Plus 108x. Now what's good about this is you can check your answer, you know, that x is equal to, at x is equal to 0, the bending moment is 0. You haven't seen an x to the 4 before like last semester, but it's absolutely a possibility, a quadratic load. Yeah, so the things to look out for there is instead of t to s, it's x to s. So sending these are like sending powers of t. That's the second thing. And the third thing is when you're coming, oh yeah, the dividing is a little bit tricky. And then when you're coming back, make sure not to come back to t, make sure to come back to x. Okay. Question 2, part 2 here. It says, hence, given that the shear is the derivative of the bending moment, calculate the shear force at x equal to 3. So that's easy. Now, I think some people actually went and solved this differential equation, but it doesn't ask you to do it. It doesn't ask you to use Laplace transforms. So just v of x is the derivative of this. Shouldn't be too bad. So differentiate this, fix the half. The derivative of x to the 4 is 4x cubed. Fix the 6, the derivative of x cubed is 3x squared. And the derivative of 108x, I'm quite confident you get that as 108. So that the shear force, I think I'm just going to wipe away this, it's kind of in the way there. Is half of 4 is 2 minus 18x squared plus 108 is the shear force. That's part 2. Oh, calculated at x equal to 3. So bang it in there, x equal to 3. Let's see what happens. Are the units knocking about? Yeah, it's going to be kilonewtons here anyway. So 2 by 3 cubed is 2 by 27 minus 18 by 9 plus 108. And we can bang that into the calculator. I don't know why I'm doing this. I know it's going to be 0. It's 0. Okay, so the shear force is 0, and surely in your final semester of level 7 civil engineering, you have to know what does it mean if the shear force is 0 at x equal to 3. What does that suggest about the location of the maximum bending moment? It's at x equal to 3. It's at x equal to 3. Now you could bang in x equal to 3 into this to get the maximum bending moment, but it's only asking about the location of it. It's just saying, well, if the shear force at 3 is 0, then that is the location of the maximum bending moment.